Part A, we have two electrical charges, A and B, a distance x meters apart, and they repel each other with a force 0.01 over x squared, 0.01 x to the minus 2. A remains fixed here, and then we're asked to find in terms of K, which I don't think K comes into this question, but we'll find the work done by the force of the repulsion by moving it from 2 to 5. Work done is force by distance, or the integral of force with respect to distance. So we have the integral of the force with respect to x should enable us to find the work done between 2 and 5, so 0.005 and 0.002. So this is going to give 0.01 x to the minus 1, increase the power, divide by the new power, so just putting a minus 1 in front or just a minus, between 0.005 and 0.002. So that's just going to be minus 0.01 over 0.005, and then minus 0.01 over 0.002. This is the same as 10 over 5, so that's going to give a minus 2, and then we're going to have a plus 10 over 2, 5. So that's equal to 3 joules for the work done. Part B is the time of death of a murdered person. It gives a lot of information, so I'm going to pause the video and let you read all the information. So, hopefully you've read it all. So we're asked to estimate the time of death to the nearest minute with all the information given. We have this differential equation, dt over t minus 21 will be equal to k dt. So we integrate these, the values that we're told, at time equals 0, the temperature was 34.7. This should enable us to get an equation in t. So this is like 1 over x, so it's the natural log of t minus 21, and the bands are t, and 34.7 is equal to kt between t and 0. So we're going to get the natural log of t minus 21 minus the natural log of 34.7 minus 21 is equal to kt. So the natural log of t minus 21 over 34 minus 21 is 13. 13.7 is equal to kt. We have our base e here, so e to the power of kt is equal to t minus 21 over 13.7. So 13.7 e to the power of kt, and then I'll bring the 21 across, plus 21 equals the temperature at any time. So what else are we told? So we're told this information here about the 31.7, and that's 90 minutes later. So t equals 90. So when t is equal to 90, we can say that big T temperature is 31.7. So that will enable us to get the unknown that we have in our equation K. So 31.7 equals 13.7 e to the power of 90k plus 21. So we're going to get 31.7 minus 21, so that's going to give 10.7. Then we're going to divide by 13.7, and that will be equal to e to the power of 90k. And using our log rules, we can say 90k by ln e is equal to ln 10.7 over 13.7. We know that the natural log of e is equal to 1, so k is going to be equal to the natural log of 10.7 over 13.7 divided by 90, and this gives k to be a negative number, minus 0.00276. So now we have our equation in full. We have temperature is equal to 13.7 e to the power of minus 0.00276 T plus 21. And we're told that the temperature is 37 when the body dies. So 37 will be equal to 13.7 e to the power of minus 0.00276 T plus 21. So it's just solving for T. The time is exactly the same math as here. So take away the 21 to get 16. Divide by 13.7. And that will be equal to e to the power of all of that guy. So minus 0.00276 T by the natural log of e equal to the natural log of the other side, 16 over 13.7. We know this is equal to 1 for repetition purposes, so this gives time to be minus 57. Negative time minus 57 minutes. So the guard arrived at 10:40, 57 minutes before 10:40 is 9:43. 9:43 for the time of death. The last part of this is a difference equation could have been used. Why would a difference equation be less accurate? So differential equations measure continuously. I think the word they want here is difference equations are what are called discrete, measured in increments, so therefore less accurate.